Welcome back. We were talking about robustness and approaches to induce robustness in the models that we are training, and we talked about a few approaches that we're trying to basically induce robustness by making sure that the model is not too sensitive with respect to small perturbations of the input data. In this part, we're going to talk about sort of a related approach, which is a very elegant approach and is referred to as distribution in robust optimization. So to motivate it, let's try to think about the previous approaches in the following way. Intuitively, what they were trying to do was to guess the data distribution during inference. And they were trying to make this guess by perturbing the input data. Okay? An alternative approach is to try to basically predict what that distribution is by directly perturbing the training data distribution. So instead of perturbing the training data itself, why not see what will happen if we train the data distribution? That's why we call this approach distribution robust optimization. Previous approaches, we were basically being robust against perturbations in the input. Here, we try to be robust against changes in the training data distribution. Okay, so here is an idea, right? So that as we've talked about numerous times, the canonical objective in machine learning and deep learning is to minimize the average loss. In particular, we basically are allocating the same weight to each data point. So it's as if you're saying that the distribution of the training data is like uniform. So I sample a training data with probability 1/n. Okay. Now, what these approaches in the field of the distribution robust optimization try to do is to say that, hey, let's generalize this uniform distribution to something like PI, and then let's try to again be robust against perturbations. In particular, they think of perturbing this 1/n to PI, and we want to make sure that we are robust against this perturbation. And by doing so, hopefully we can have a good estimate of what the data distribution at inference will be. So therefore, the model is going to enjoy high performance during inference. Okay. Now, like before, where we sort of impose a bound on our perturbation. So if we are looking for maximum perturbation, we impose a bound on its norm. If we are looking for random perturbation, we would impose a bound on the variance of our perturbation. Essentially, it's the strength. Here, again, we should also impose a bound on the amount of perturbation we are introducing. And a natural way to talk about that is to talk about the difference between the perturbed distribution, P, and the uniform distribution, 1/n. Okay, so we're talking about the distance or the divergence between probability vectors. So therefore, natural notions of distance, such as KL divergence, will be applicable here. Okay, so notions such as the Euclidean norm perhaps are not a good idea to be used here. All right. So therefore, we are perturbing the input distribution, and we want to make sure that the perturbation is basically bounded according to some nice notion of divergence. Okay. Equivalently, this is basically what we are trying to do. Okay. So let us define sort of a confidence set. A confidence set P, which is basically all distributions that have a bounded perturbation with respect to the uniform distribution. Okay, so we define this, and then we want to find a model that is robust against the worst case perturbation as quantified by our notion of divergence. So basically, we're going to go and search over the distributions in this confidence set, calculate the loss, and then we want to minimize the worst case loss. Okay. So here's my way of demonstrating this, right? So this is our confidence set. Let's imagine that there are, for instance, in this case, 7 distributions here. So I'm going to go basically see which one of these distributions will result in the worst loss. Then I'm going to use that as my training distribution, and then apply my favorite optimization algorithm, such as SGD with momentum. Okay, so that's the main idea. So therefore, as you can see, we are being sort of robust against perturbations in the data distribution as opposed to the training data itself. So before moving forward, one other thing I want to point out here is that, like before, we can talk about random perturbation as well. So here we are looking for the worst case perturbation. So you could think of basically defining something like an expectation over the distributions that belong to the confidence set. And in some sense, this approach is less pessimistic compared to what I'm depicting here, that looks for the worst case perturbation. All right. So let's go over a simple example. Let's assume that we are using KL divergence to quantify the perturbation we are introducing with respect to the uniform distribution. Okay. And as a reminder, the KL divergence is given by this expression. Okay. Now, after certain steps, again, our idea is that we want to see what's that inner maximization problem, and whether that leads to a closed form expression such that we basically can again think of our DRO problem as a version of empirical risk minimization, similar to the examples we discussed in the first part of the lecture. Okay, so it turns out we can actually do this after certain steps that I'm omitting here, which crucially rely on using tools from duality theory, something we haven't talked about in this course. We can basically show that our DRO problem is going to reduce to what I'm showing here. Okay, so it is nonlinear. So naturally, it depends on our notion of perturbation, or the strength of perturbation rho. You can see it here and here, but it also involves terms such as log and exponential. Okay. So for those of you who are familiar with convex optimization, this is sort of related to the log sum exponential. Okay. So in particular, the log sum exponential is related to the Fenchel dual of the KL divergence. That's why we basically arrive at this expression, but that's not important. Okay. So what's important is that after again some steps, we can arrive to this equation. Okay. Now let's do some checks. Okay. So I'm going to see. So I want to see what will happen when rho goes to 0 and when rho goes to infinity. In particular, I want to see what will happen when I don't introduce any perturbation, and when my perturbation is significant. Okay. For the first case, it is natural to expect that the loss has to reduce to the original empirical risk minimization, meaning minimizing the average of the loss over the training data. Okay, and indeed that's actually very simple to do. Okay, and show that when rho goes to 0, the objective reduces to the average loss, which we can think of it as the non-robust case, very natural. While when rho goes to infinity, or when the rho becomes large, the loss will reduce to the maximum sample loss. So this basically is saying that ignore everything, every data point in your data set. Just make sure that you are finding a model that fits the sample with the worst loss. Okay, so in some sense, this is very, very pessimistic and robust. Okay, so it's pessimistically robust. So therefore, if we choose a row in the middle, we are sort of interpolating these two extreme cases, the non-robust case and the highly pessimistic case. Okay, all right. So that's one observation we can make. Another observation is related to how we can sort of solve this, and how is this related to the to an ERM problem. Can we think of it as some ERM problem? And the answer is actually quite elegant. So note that we have a log operator here. Log is a function that is monotone. So if I were to plot the log, so this is log x, it's going to be something like this. Okay, so it's monotonically increasing. Now, in optimization, when we have composition of a monotone function and another function, and we want to minimize it, it turns out that that problem is going to have the same solution when we remove the outer monotone function. So therefore, since log is monotone, our problem here is actually equivalent to what I've written here, where I get rid of the log, and also I get rid of the constants such as such as rho inverse. Okay, all right. So why this is useful? Well, we can actually call what I have here to be L tilde, and in that case, then this is kind of like a new empirical risk minimization. I'm minimizing some average loss, but my average loss is actually a transformed version of the original loss function. I'm using the exponential to sort of add more weights to samples with higher loss value, and sort of reduce the weights of samples with the low loss value. Okay, so this again in some sense shows that we are inducing some robustness. All right. So we can also talk about this. So weighing samples according to the loss value by looking at the gradient-based algorithms for this kind of a problem. Okay. So let's consider the original loss before removing the log. Okay. And let's calculate the gradient for this problem. And the reason we calculate the gradient is basically the fact that we utilize gradient-based optimization algorithms to minimize this loss and therefore train our model. Okay, the gradient is actually is easy to calculate using the properties of the log functions and the exponential function, and it's going to be given by this expression. Okay, so I think a simple way to think about this is as I've written here. So it is kind of like a weighted sum of the individual gradients, where the weight is given here. So the weight, as you can see, is sort of proportional to the loss value. Okay, so what this means is that the samples that have larger loss value are going to have a larger weight. So therefore, when I use the gradient in my update, the model is going to try its best to fit them better compared to the samples that have lower loss value. Because for those cases, for those samples that have a lower loss value, their weights alpha will be smaller. So which means that the update vector that I'm using in my gradient-based method is not going to put like a lot of emphasis on them when updating the parameter. So this again shows that we can think of our problem as a weighted empirical risk minimization problem, where the weight of each sample depends on the parameter as well. So it's given here. The weight is larger if the sample is suffering from a higher loss, and the weight is smaller if the loss value is small. So the weights are sort of designed thanks to using the scale divergence as a way to quantify the amount of perturbation we're adding. The weights are designed to promote samples with higher loss value, meaning that the model wants to make sure that it performs really well on samples that have a high loss value compared to the ones that don't have a high loss value. Therefore, we are, by doing this, we are inducing robustness into our training process. Okay, so this was a short overview of some elegant ideas when it comes to to inducing robustness into deep learning models. As we saw, many of the problems reduce to some constraint optimization problems or some regularized optimization problems. So in the next lecture, then we want to talk a little bit about systematic ways to solve optimization problems in the context of deep learning training, where in addition to having an objective, of course, we also have some explicit constraints. So this is something we haven't talked about before, but it's worth it to spend some time to think about these principal ideas. I'll see you in that lecture.